Okay, so we were solving this problem last Thursday, and let's continue. So we have a reheat cycle, ideal reheat cycle, and this is the schematic of this ideal reheat cycle. So you can see there are high pressure turbine and low pressure turbine, and number 3 and number 3 and number 2 and number 3. This is the reheat process, and this is the TS diagram. So the first thing we want to do is we are going to determine the specific enthalpy at each state, number 1, 2, 3, 4, 5, and 6. And we found two specific enthalpy values. They are H1 and H3 because we know the pressure and temperature at number 1 here. And we also know the pressure and temperature at number 3. So today we are going to start with number 2 and number 4, then the rest. So let's determine H2. We know the pressure is T2 is 6 megapascal. However, we have no other information. So let's read the problem statement to find to see how we can determine H2. If you read here, it says each turbine stage, either high pressure turbine or low pressure turbine, has an isentropic efficiency of 78%. So I guess we can use this number to determine H2. It sounds a little bit complicated, but if you remember the isentropic efficiency equation from chapter 6, it's not that difficult. So let's do that together. The isentropic efficiency can be determined by, so the isentropic efficiency of a turbine can be determined by comparing the power produced by an ideal turbine and the power produced by an actual turbine. So one of them is going to go to the denominator and the other one goes to the numerator. So you need to determine which one is greater than the other between the turbine power produced by an ideal turbine and the turbine power produced by an actual turbine. Of course, the ideal turbine is going to produce the largest power. So we can say the turbine power produced by the ideal turbine. So I'm going to say S to show that this is isentropic turbine, the ideal turbine, and the actual power is going to be less than the ideal turbine. So I'm going to say WTA. So that's how we determine isentropic turbine efficiency. And this is what? 78%, 0.78. Then, how can we determine turbine power? If you look at this turbine, we have one inlet and one exit and one power output. So the energy balance equation for this high pressure turbine is going to be W dot T of high pressure turbine is going to be M dot times between 1 and 2 for the high pressure. And between 1 and 2, 1 is greater than 2 because this turbine produces power. So that power comes from this 1. So H1 should be greater than H2. So it is H1 minus H2. So that's how we determine turbine power. Now we need to think, how we can, apply this one for the denominator and for the numerator. The turbine power produced by the ideal turbine can be determined by m dot H1. That is, H1 is the inlet condition. So regardless of this turbine, H1 should be the same between the isentropic turbine or the actual turbine, because this H1 is before entering the turbine, right? The only difference between isentropic turbine and the actual turbine is going to be the output. So the H2 is the one different. So H2 of the isentropic turbine, I'm going to say H2, assuming isentropic turbine H2S. And H2 of the actual turbine, I'm going to say just H2. And we want to determine this H2. Then we already know, and by the way, we can tensor m dot out, and we already know what is H1. Here, 3,192.3. Same goes here. And can we determine H2S? Yes, we can. We can assume that the entropy does not change between 1 and 2, and that's how you can determine H2S. So let's do that. The specific entropy, specific entropy at number 1 can be determined by from this pressure and temperature. This is a superheat vapor. So let's go find 28 megapascal. And 520 degrees Celsius. So we have 28 megapascal, 520 degrees Celsius, and specific entropy value is going to be this one, 5.9566. 5.9566 kilojoule per kilogram Kelvin. Now, we can use this S1 and this pressure, 6 megapascal. And from these two, we can find H2S. Okay? So let's do that. First, we need to determine the phase change process at state number 2, assuming isentropic turbine. Then we need to determine the phase change process. We are going to use TS diagram. At 6 megapascal, TS diagram looks like this. We need 3 property values: T set, SF, and SG. We can find them from 6 megapascal. So let me go find 6 megapascal. It's right here at 6 megapascal. At T set, I'm sorry, that's a superheat vapor table. 6 megapascal. It's right here. 60 bar is 6 megapascal. T set is 275.6. And SF is this number, 3.0267. Sg is this number, 5.8892. And on this TS diagram, we have compressed liquid here, saturated liquid, saturated mixture, saturated vapor, and superheated vapor. And now it's time to determine the phase change process. What is the specific volume? 5.95. So let's find this specific entropy on this TS diagram. 5.95 is greater than 5.88. So slightly on the right. And the phase change process is going to be superheat vapor. So once you determine that we have a superheat vapor, you go to superheat vapor table at 6 megapascal. So here is 6 megapascal. And the specific entropy, specific entropy is 5.95. 5.95 is between these two values. So the H value at this specific entropy is going to be between these two values. So what you need to do is we need to do a linear interpolation to determine H2S. So if you do, H2S is where are you? 2822.2. So from table A4, H2S is going to be 2822.2 kilojoule per kilogram. This H2 goes here. And since the isentropic turbine efficiency is 0.78, we have everything but H2. So from this, H2 is 2903.6 kilojoule per kilogram. Okay. So this is a little bit complicated because we have an isentropic turbine efficiency. So the only extra step is using this equation. And you remember how we determine H2 from the standard ideal Rankine cycle assuming isentropic process, but we are going to use that process to determine this H2S. And then use this isentropic efficiency equation to determine the actual H2. So from here, we get this H2. It is 2903.6 kilojoule per kilogram. Just feel free to let me know if you have any question, okay? These are for H2. Now let's determine H4. How can we do that? What we know, by the way, H4 at state number 4, the only thing we know is that the pressure of the condenser. So what is the condenser pressure? the condenser operates at constant pressure 6 kilopascal. So this is P4. So let's go back. P4 is 6 kilopascal. That's the only property value we know. So we need to find another clue to determine H4. And it says that each turbine stage, but this time low pressure turbine, has also an isentropic efficiency of 78%. So we are going to follow the same step here to determine H4. So whenever you have an isentropic efficiency other than 100%, this is what you need to do. So I'm going to repeat this one, this time for H4. So the isentropic turbine efficiency, which is 0.78, can be determined by this equation, m dot h1 minus h2. No, this time between 3 and 4. So h3 minus h4 divided by m dot h3 minus h4, assuming isentropic process, H4S. So from this equation, we already know H3, which is 3,422.2. So this one is also 3,422.2. We just need to determine what? H4, assuming an isentropic process. So let's do that. If you want to determine, the H4 assuming isentropic process, we have a P4, and we are going to use this assumption. S3 is the same as S4. It is an isentropic process. So what is S3? We can find S3 directly from pressure and temperature. We know pressure is 6 megapascal, temperature is 500 degrees Celsius. So let's go to superheat vapor table. So here is the superheat vapor table. We have a 6 megapascal and 500 degrees Celsius. So what is the specific entropy? This one, 6.8803. 6.8803 kilojoule per kilogram Kelvin. So how many property values do we have? We have S4 and we have pressure P4, which is 6 kilopascal. Since we know two property values, can we determine H4S? Yes, we can. So let's do that. The first thing we need to do is that we need to determine the phase change process. So let me make TS diagram. TS diagram at 6 kilopascal. Going to look like this. And we need to know three property values. They are T set, SF, SG. So let's find them from the pressure table. Here is the pressure table, and we have 6 kilopascal right here. T set is 36. 36.16, and SF is this one, 0.521, 8.3304, 0.521, 8.3304. 4. Okay? Then on this TS diagram, we have compressed liquid here. This point is saturated liquid, saturated mixture, saturated vapor, and superheated vapor. Then we know the specific entropy, 6.88. So let's find this value on this TS diagram. 6.88 is greater than SF and less than SG. So it's going to be between these two. What is the phase change process? Number 3. So 6.88 is somewhere around here. So the phase change process is going to be number 3. Saturated mixture. If you have a saturated mixture, how can you determine its phase change process? I'm sorry. How can you determine its property? We need to know one more property, which is quality X4. So let's determine X4 first. We can use a linear interpolation. Let's use a linear interpolation for entropy S. S4 is SF plus quality X4 times SG minus SF. So what is S4? 6.88. 6.8803. What is SF? 0.521. 0.521. SF 0.521. What about SG? 8.3304. 8.3304. So we have everything but quality X. So can we determine quality X? Yes, we can. The quality X is 0.81 43. 0.8143. Then we are going to use this quality X to determine H4S. Then let's determine H4S by using linear interpolation. HF plus quality X4 times Hg minus HF. Where can we find HF? At the given pressure, 6 kilopascal. At 6 kilopascal, HF is going to be 151.53. 151.53. Hg is 2567.4. HF is 151.53. And we have the quality X that goes right here. So we can determine H4S. H4S is 2405.5 kilojoule per kilogram. This number goes here. 2405.5. So we have everything, but the actual H4 that we can determine. The actual H4 is, so up to here, the actual H4 is I'm sorry, I made a mistake. This H4S is not this value. H4S is 2118.8. So this one is 2118.8. It's also 2118.8. Then H4 is 24 or 5.5 kilojoule per kilogram. So this section is for H4. Then H5. H5 on this green, it is saturated liquid. So when you have saturated liquid, at what pressure? The pressure is going to be the pressure of the condenser. So P5 is 6 kilopascal, and this is phase change process number 2, saturated liquid. Therefore, H5 is going to be HF at 6 kilopascal. That is this one, 151.53. 151.53 kilojoule per kilogram. That was simple. Now H6. Unfortunately, I don't have space, so let me use another paper. So let's look at this H5. H5 is the inlet of the pump. So we have a pumping power goes in, and the exit is number 6. And let's see, what is the pressure? The pressure P6 should be the same as P1, and P1 is 28 megapascal. So the pressure is going to be 28 megapascal. So P6 is 28 megapascal. But that's all we know. So what can we do? If we go to the problem statement, it says the isentropic pump efficiency is 82%. So unfortunately, we have to do this again. So let's find the equation for isentropic pump efficiency. It's going to look similar to this isentropic turbine efficiency. But let's see. Isentropic pump efficiency can be also determined by the power, the pumping power. There are two pumping powers. One is the ideal pump, and the other one is the actual pump. So for the same, the pumping job, which one is going to spend less power? Of course, the isentropic pump is going to, consume the minimum power for the same pumping, right? So this pumping power by isentropic pump is going to be less than the actual pump. So how can we determine W dot P according to the energy balance equation? So W dot P is going to be M dot times the difference in specific enthalpy between 5 and 6. The pumping power is added. Therefore, H6 should be greater than H5. So the energy balance equation is the pumping power can be determined by M dot and H difference. But this time, H6 is greater than H5. So it is H6 minus H5. And as you know, as you know, the isentropic pump is going to consume less power. So that goes to the denominator, and that goes to the numerator. M dot H6, but this one is isentropic pump. H6S minus the inlet should be the same, H5, divided by M dot of the actual H6 minus H5. So that's the equation. And this pump, isentropic pump efficiency is 82%. So this one is 0.82. We can cancel M dot and H5 should be the same, that because this is the inlet of the pump. So regardless of whether the isentropic or actual pump, the inlet conditions do not change. So it's going to be 151.53. 151.53. So now the question is, how do we determine this H6? If you remember from the previous, the standard Rankine cycle, do I have that? Do I have that one? We learned the exit of this isentropic pump can be determined by H5 plus specific volume V at the inlet times pressure difference, P6 minus P5. I think, I show you this equation last Thursday and told you to write it down on your formula sheet. Of course, at the time, that wasn't a reheat process. So the number was H4 is H3 plus V3 times P4 minus P3. We are going to use the same equation, but between 5 and 6. So what is H5? We know 151.53. What is the specific volume of saturated liquid at 6 kilopascal? At 6 kilopascal, this is the specific volume, 1.0064. 1.0064 times 10 to minus 3 cubic meters per kilogram. So let me write all the units. And P6 is the pressure in the steam generator, 28 megapascal. But you don't like megapascal, 28,000 kilopascal. And P5 is the pressure of the condenser, which is only 6 kilopascal. That's how you determine H6S. So this one, after you calculate this one, by the way, I don't know the value. This one goes in here, H2S. That will give us 86. I know this value, by the way. It is 185.89 kilojoule per kilogram. This one goes in here, 185.89 kilojoule per kilogram. So that's how you determine H1, 2, 3, 4, 5, and 6. Okay. I know this one is a little harder than the previous problem because of this isentropic efficiencies, pump efficiency, and two turbine efficiencies. But the process is the same. We are going to use this isentropic efficiency equation, and we are going to follow the same step as we did in the previous problem to determine this H of S. And that's how you determine the actual specific enthalpy. Okay. So once you determine all these H values from 1 to 4, now you can solve this problem. Then what is the problem? Determine the quality of the steam exceeding the second stage of the turbine. What? So we want to determine the quality of the steam exceeding the second stage of the turbine. So we want to determine the quality of H4. So how can we determine that? By using the specific enthalpy at number 4. So the specific enthalpy at number 4 is 2405.5. So let's find X4. By the way, just for your information, this X4 that we are going to determine is different from this X4. This quality X4 is when we assume that this is an isentropic process. You see this, the subscript S. So we solve this, equation to determine this H4S, assuming an isentropic process. However, in reality, it is not an isentropic process. So you can recalculate this X4 by using this actual specific enthalpy H4. So let's do that. So how can you determine this quality X? Always use a linear interpolation. So what kind of linear interpolation? H4 is HF plus quality X4 times HG minus HF. So how do we determine HF and HG at the given condition? What is the condition do we have? 6 kilopascal. So we are going to determine, we are going to find HF and HG from 6 kilopascal. Here we have 6 kilopascal. HF is 151.53. HG is 2567.4. So let me write these two values in this equation. So HF is 151.53. HG is 2567.4. HF again 151.53. What is H4? 2405.5. So we have everything. Now, can you determine quality X? Yes, you can. So quality X4 is going to be 0.933. And the last question is the thermal efficiency. How do we determine the thermal efficiency? The thermal efficiency can be determined by net power divided by heat transfer in So how do we determine net power? How many powers do we have? I wish I have a larger screen. So how many power do we have? We have pump power, turbine power in the high pressure turbine, and turbine power from the low pressure turbine. So there are three. Two turbine powers are the one that we produces. So that's going to be positive. The turbine power W dot T HP plus W dot T LP and minus, we are going to consume pump power, minus W dot P. And how many heat transfer in? There are two. One is between 6 and 1. The other one is between 2 and 3. Q dot in 6 and 1 plus Q dot in 2 and 3. So if you know how to determine each the each power and the rate of heat transfer, you can determine the thermal efficiency. So how can we do that? Let's find this one first. The power produced by high pressure turbine, it is between 1 and 2. So it's going to be either m dot H1 minus H2 or H2 minus H1. But as you know, the turbine produces power. That power comes from number 1. So H1 should be greater than H2, right? So it's going to be H1 minus H2. What about this turbine power from the low pressure turbine? It's going to be between either H3 minus H4 or H4 minus H3, but as we know, it produces power. This power comes from H3, so H3 should be greater than H4. H3 minus H4. What about this pump power? It is between 5 and 6, so it's going to be m dot either H5 minus H6 or H6 minus H5. So the pumping power goes in, so it's going to be added to number 5. So number 6 should be greater than number 5. So it's going to be H6 minus H5 divided by heat transfer between 6 and 1. So that's going to be m dot either H6 minus H1 or H1 minus H6. But as you can see, Q in is added to H6 to become H1. So H1 should be greater than H6. So it's H1 minus H6. What about Q in 2, 3? It's going to be either H2 minus H3 or H3 minus H2. But as you can see, H2, the Q in is added to H2 to become H3. So H3 should be greater than H2. So this is how you determine the thermal efficiency. We can cancel m dot and H1 here, H2 here, H3 here, H4 here, H6, H5. So everything is given. We already found them. So you can calculate the thermal efficiency. Okay. By the way, I don't know the thermal efficiency. It's not given here, but you can calculate them, right? Any question about this problem? This is the hardest problem in this chapter. So if you can solve this one, then no worry in the final exam. So this one has 3 isentropic efficiencies. That's why it took so much time, and that's why it looks complicated. You will see at least one problem from this chapter in the final exam. It may have isentropic efficiency, but not 3 of them, maybe 1. Very unlikely 2, but 1 for sure. Okay, maybe pump has a 100% efficiency, so you don't need to worry about isentropic pump efficiency. But I may say the turbine has this isentropic turbine efficiency, or the other way, the pump is not isentropic turbine, but turbine is, or the other way, the turbine is not an isentropic turbine, but pump is. So you can at least do one. You can at least, use one isentropic efficiency equation. Okay. That's everything about chapter 8. Any question? No? Then there's a new homework assignment. Any homework, any remaining homework is going to be due by the final exam date. So you have plenty of time to prepare them. This is the last chapter, gas power systems. So in this chapter, we are going to study three thermodynamic cycles. They are gasoline engine, such as Otto cycle. And the other one is diesel. The last one is gas turbine. All 3 are very widely used in engineering. But we are not actually, studying each cycle. We are just learning how we can apply the thermodynamic equations that we studied from chapter 3 to 6, and to, learn, any application where we can use these equations. So we just want to, see how we can use thermodynamic equations in real engineering applications. First of all, we are going to focus on Otto cycle and diesel cycle. So we are going to briefly go over how reciprocating internal combustion engines work. So there are 2 different types of combustion engines. One is spark ignition, and the other one is compression ignition. The spark ignition is, the most likely, your car engine, the gasoline engine. So the way it works is that, inside the engine room, we are going to, provide fuel and air mixture. So the mixture enters this piston cylinder device, and there's a spark plug is going to, ignite, so that the mixture undergoes combustion. That is spark ignition. On the other hand, compression ignition is diesel engine, and in this case, we don't provide a mixture of fuel and air. Instead, only air enters this piston cylinder device, and the piston is going to compress this air up to a very high pressure and temperature. And at this time, the fuel is going to be injected. And because of the high pressure and high temperature, combustion occurs spontaneously when the fuel is injected. So there's no spark plug in a diesel, the engine. Then what is the, the main difference? Why do we, use two different combustion engines because each has pros and cons. The good thing about gasoline engine is that it's very simple and therefore it can be lightweight and relatively low cost. Usually good, at about the 300 horsepower, which is 225 kilowatt. On the other hand, combustion ignition, which is a diesel engine, is preferred for high power application and also when fuel economy is required, because we are going to talk about how we can increase, how we can enhance the thermal efficiency to achieve the high fuel economy for combustion ignition, which is all about compression ratio, and we are going to study later. So we are going to study thermodynamic cycles for spark ignition system and compression ignition system, so two different types. And to do so, we need to learn briefly about how this piston cylinder device look like. The first one is called displacement volume. Displacement volume is the volume swept by this piston. So this piston moves up and down. So it goes up and then it goes down. So the entire volume, which is swept by this piston, is called displacement volume. And the other one is compression ratio, which is very important when we study internal combustion engine, because this one determines fuel economy. So compression ratio is the volume ratio between the top dead center. The top dead center means that when the piston is at the uppermost position, and the bottom dead center means when the piston is at the far down here. So the volume occupying this piston cylinder device, the ratio between these two is called compression ratio. So it can be calculated by the volume at bottom dead center divided by volume at top dead center. So the volume when the piston is at the bottom dead center, the largest volume, divided by the volume when the piston is at the top dead center. It's going to be the minimum volume. So the maximum volume divided by minimum volume, that is the compression ratio. And usually when compression ratio goes up, the thermal efficiency goes up. So the more we can compress, the higher the efficiency we can obtain. However, there are some limitations, but in general, the higher compression ratio means the higher efficiency. Then how can we, what happens when we have high compression ratio? Since we are compressing more, we can achieve higher pressure and higher temperature of the system. If you want to have high pressure and high temperature gas, the problem is that if you compress fuel and air mixture up to high pressure and high temperature, they can undergo combustion without any the spark or something. So when we use a gasoline cycle, we cannot go to high pressure, high temperature because we have a fuel already inside. But instead, in the diesel engine, we don't have a fuel inside. We only have a gas. We only have air. So we can compress as much as we can. And then, we inject the fuel so that we can, we can have a combustion at extremely high pressure and high temperature. That's how we can increase the compression ratio, and that's how we can achieve higher thermal efficiency. So in general, diesel engines are more efficient than gasoline engine. But it has, also, yes. That depends on the geometry. That depends on, how you design your pistons and the device. So some people like to make this piston, a large, like a thick, or some people like to make this piston cylinder device tall. Then what is the difference? When you make it tall, that means that you have more piston moving up and down, right? So that will increase the compression ratio. So when you want to achieve higher pressure, a higher efficiency, the one of the way is going to make it it's as tall as possible. Then is it always the good? Not necessarily. The problem is going to be when you make it tall, there's a more time is required for the piston is moving up and down rather than the short one. So the same, the engine volume, one, the piston is moving up and down for a long time, and the other one is going to be short. The good thing about long is going to be you have a high compression. That means that the efficiency is going to be good. But the bad thing is that each time it delivers power, it's going to be slow. So one time you kick the tank, so it runs, but it takes the one round of the piston up and down and goes back. Then there's another kick. So there is a interval between each power is provided. On the other hand, when you have a the short cylinder, the more frequent movement of the piston. So each time when the crank is rotating, when the wheel is rotating, you have a power delivered. So this depends on the where you want to what is the application of the engine that determines the shape of the design of this piston cylinder device. So in general, let's say that you want to do the high, the speed, like a high speed, the sports car. Then you want to have, you don't care about, the efficiency. You want to, you want to have, the more power is delivered, less frequency. So you can make the piston short and thick, so that you can, have more. So in that case, the usually RPM goes high when you make this piston short. You know that when you drive, the sports car, usually RPM for sports car is way, the higher than general, like a commercial sedan, right? So those, the engines are short but thick. On the other hand, if you want to, the design a dump truck or anything works in construction, the thing we care is not about, how fast this dump truck goes. We want to, the save energy. Then this engine can be tall. When we care about fuel economy the most? When you design a container ship. Have you seen the engine room in a giant ship? The engines are pretty tall, so you can have the long distance. The piston is moving up and down. Why is that? We want to have higher compression. Then we can increase the compression ratio, so we can save the fuel. So the way that we design an engine, it depends on the where we are going to apply. So it's going to be the balancing between the fuel economy and the power output. Yes. Oh, okay. So in a gasoline engine, the compression ratio is limited. We are going to talk about that later, but just giving you a heads up. So the compression ratio is limited in a gasoline engine. On the other hand, diesel engine, that that limit, we don't need that limit. So you can go higher compression. The reason is that when you have a gasoline engine, you have a fuel and air mixed together. and then it is injected in the the piston cylinder device. So if you want the conversion occurs when the piston is at the top dead center. That's when you have a minimum room. So when combustion occurs, when you have the minimum volume, that's when you can produce the maximum power, right? You don't want to have a conversion when the piston is bottom dead center. It's not gonna produce any work, right? So you want to make sure that the timing when the spark ignites the air fuel mixture is gonna be right at this time, right? But if you increase pressure, increase temperature without this spark, the air fuel mixture may self-ignite. That is called knocking. You don't want that happens. So in a gasoline engine, you cannot just increase the compression ratio. If you go to above a certain limit, that knocking problem is going to occur. So usually air fuel mixture in a gasoline engine is pretty limited. On the other hand, diesel engine, you can go higher compression ratio so that you can achieve higher fuel efficiency. But that sounds like, okay, diesel engine is always good because we have a higher compression ratio, we have a higher efficiency. But there is also, the side effect. What is the side effect? The air in the environment consists of mainly two, nitrogen and oxygen. And what we assume is that the fuel that we inject in the engine is a carbon hydrogen. So it's going to be C and H, and that's it. C is some numbers and H is some numbers. So it can be propane, octane, and butane, etc. Right? So what we expect is this carbon becomes carbon dioxide. This H, hydrogen, becomes water. By the way, you are going to study that when you go to EGR356, Thermodynamics 2. But just to, since you asked. But so that is our assumption. When we have a carbon in the fuel, it becomes carbon dioxide, no problem. When we have a hydrogen in the fuel, it becomes hydrogen, oxygen together, water, so no problem. But when you use diesel engine, because of the compression ratio, because of fuel efficiency, you want to increase pressure as much as you can. Then what is the problem when we go to, and when we have a combustion at extremely high pressure? The nitrogen gas usually is called inert gas. They don't react in general, but at high pressure, they react. So nitrogen is going to react with oxygen, and then that produces what? Air pollution, which is very dangerous. That's what makes all the the air pollutions. So that's why when there are many diesel engines, we talk about all the air pollutions. That is because of this high pressure. So high pressure means high efficiency, but bad for the environment. So everything in engineering is more like the balancing. So previously we are talking about efficiency and output, right? You're balancing this one. Now you're talking about efficiency and environmental effect. So everything, when you design any engineering product, it's not going to be, it's not just one-way road. It's going to be two-way. So you need to balance, the road should be larger than the other. Okay? That answer everything, right? Okay. So we are going to, so what we learn is that, when we increase the conversion and compression ratio, we can achieve higher efficiency. The reason is that, that we can have a conversion at high pressure and high temperature. Then, let's talk about how these internal combustion engines work. There are two different, the cycles. One is a 4-stroke cycle. The other one is a 2-stroke cycle. Most cars that you drive are 4-stroke cycle, and usually when you drive a bike or something like a small engines, or the gasoline gas powered, the lawnmower, they are two-stroke engines. But in this course, we're going to focus on four-stroke engine, okay? By the way, we are not actually studying, the four-stroke engine. We are just briefly go over how they work, and what we are going to focus on is going to be how we can use our thermodynamic equations to study them, okay? So we are going to talk about how we can simplify this internal combustion engines using isentropic process, constant volume process, or constant pressure process, or anything that we studied from chapter 3 or 4, so we can apply energy balance equation and entropy balance equation. That is the main part of this chapter, okay? Actually, if you are, curious about these materials, you can go to Google, and there are many, the visualized, the lectures are available, which is more interesting. But we will just go over briefly, because if you want to simplify this, the internal combustion engines to apply thermodynamics equation, we need to know at least, what other processes are available. So we are going to focus on this four-stroke cycle. This four-stroke cycle consists of course, four strokes. The first one is power stroke, and compression stroke, and intake stroke, and exhaust stroke. So it's easy to explain, using this, the figure. So the first one, we usually start with compression stroke. Compression stroke means the piston is at the bottom dead center. So the piston moves bottom dead center, and assuming that we have a air-fuel mixture already inside. Do you want to have a combustion right away? No, we want to move this piston upward so we can compress the air-fuel mixture, so its pressure goes up, its volume goes down. Its pressure goes up. By the way, this is a PV diagram. PV diagram. So when this piston moves upward, we can say, okay, pressure goes up, but volume goes down, so this way. And then once it reaches the top dead center, then spark is going to ignite. So the combustion occurs. When there's a combustion occurs, what's going to happen? The pressure is going to increase dramatically, and temperature increase dramatically. So there is an expansion from the top dead center to the bottom dead center. So pressure goes down and volume goes up. This is the process. This is the process when we deliver power to the crank. So that's when we deliver the power. So the combustion occurs, and it's going to push this piston downward. That is power stroke. Once it hits the bottom dead center, now what's inside? Do we still have an air-fuel mixture? Not anymore. Now we have an exhaust gas. So we want to get, remove this exhaust gas out of this piston cylinder device. How can we do that? Now we are going to open exhaust valve and then move this piston upward. So this exhaust gas goes outside. That is called exhaust stroke. So once the power stroke is over, then exhaust stroke. At constant pressure, since the valve is open, we are going to pushing this, the exhaust gas out of this cylinder. That is exhaust stroke. Then once it hits the top dead center, exhaust valve is closed. Now the intake valve is open, and it's going to move downward. So there's a negative pressure. Air-fuel mixture is going to add it. And when it hits the bottom dead center, is now the time for the compression stroke. Okay? So out of these four strokes, there is one stroke that delivers power. Okay. What about two-stroke cycles? Smaller engines operate on two-stroke cycles with intake, compression, expansion, and exhaust accomplished in one revolution of the crankshaft. Is it good or bad? It's good because it's simple, you can make it small. It's bad because its efficiency goes down. Okay. And one of the the important the performance parameter is called mean effective pressure. Mean effective pressure can be determined by the net work divided by displacement volume, and this can can be used. The higher mean effective pressure would produce the greater net work for the same displacement volume. That is what I told you. When you make it taller, the compression ratio goes high, so that that you can produce more the power, more work for the same displacement volume. Okay. But that's the brief information about internal combustion engines. The detailed study of the performance of reciprocating internal combustion engine requires consideration of complexities, including these. What that means. In reality, it's going to be very complicated. So you cannot, analyze internal combustion engine by hand. So we usually require computer simulation. So what we are going to do? We are going to use a simplification of reciprocating internal combustion engines that is called air standard analysis. And we are going to study air standard analysis after we come back from Thanksgiving. Okay? Any question for today? No? Then happy Thanksgiving and see you on Tuesday.